Good morning, everyone. Today I bring you chemical bonding, class 11, chemistry. In this chapter, we have learned that more energy and less stable. It means the compound which having more energy, they are less stable because they want to complete their octet. तो जितने भी एलिमेंट्स होते हैं अगर वो अपना ऑक्टेट कंप्लीट करना चाहते हैं तो इसके लिए उनको एनर्जी कंज्यूम करनी पड़ती है और लूज करनी पड़ती है. तो हाउ डू एटम्स अटेन द लोएस्ट एनर्जी एंड टेन टू बी एन स्टेबल? बाई लूजिंग द एनर्जी. यूनिवर्स में कंपाउंड्स स्मॉल स्मॉल एनर्जी का यूज़ करके एक लार्ज कॉम्प्लेक्स कंपाउंड बनता है. फॉर एग्जांपल फोटोसिंथेसिस. फॉर एग्जांपल ग्रेफाइट्स. ग्रेफाइट में छोटे छोटे एटम्स जो कि कार्बन के होते हैं, जब वो कंबाइन होते हैं तब हमारा एक लार्ज मॉलिक्यूल्स बनता है. वाटर मॉलिक्यूल्स में दो एटम्स कंबाइन होते हैं हाइड्रोजन के ऑक्सीजन से. एंड सेम एज मीथेन में अगर मैं बात करूं पीरियोडिक टेबल की, तो पीरियोडिक टेबल में नोबल गैस आर स्टेबल एंड इनका जो कॉन्फ़िगरेशन है हीलियम को छोड़कर सबके आउटर कॉन्फ़िगरेशन में 8 इलेक्ट्रॉन्स होते हैं. इसीलिए एवरी एटम इन द पीरियोडिक टेबल वांट टू बी स्टेबल इलेक्ट्रॉनिक कॉन्फ़िगरेशन लाइक हीलियम. टू एटम ऑफ एनी कंपाउंड्स व्हेन कंबाइन दे मेक द मॉलिक्यूल्स. तो एटम की जो एनर्जी होती है वो मोर एनर्जी होती है बट वो लेस एनर्जी में कन्वर्ट हो जाते हैं बाय बॉन्ड फॉर्मेशन. तो एक लेस एनर्जी वाले एटम जब कंबाइन होते हैं तो वो एटम्स या मॉलिक्यूल्स बनाते हैं. तो बॉन्ड फॉर्मेशन लोअर द एनर्जी की वजह से होती है. एटम कंबाइंस होते हैं ऑन द बेस ऑफ केमिकल बॉन्ड. अकॉर्डिंग टू लुइस एंड कॉसल, इन्होंने क्या बताया कि जब भी दो एटम कंबाइन होंगे तो वो एनर्जी यूज़ करेंगे. तो एनर्जी जो होती है वो इन द फॉर्म ऑफ न्यूक्लियर फोर्स. अगर हम बात करें नोबल गैस की, तो इलेक्ट्रॉनिक कॉन्फ़िगरेशन नोबल गैस का सभी में आउटर इलेक्ट्रॉन 8 है, यानी कि 1s2, 2s2, p6. तो 3s2, p6, 4s2, p6 एंड 5s2, p6. ये सारे के सारे ऑर्बिटल कॉन्फ़िगरेशन है. बट हीलियम में 2 है क्योंकि इसका डुप्लेट कॉन्फ़िगरेशन होता है. तो जब हीलियम का डुप्लेट कॉन्फ़िगरेशन है तो सारे के सारे एग्जिस्ट इंडिपेंडेंट इन एटॉमिक स्टेट.
On the contrary, the remaining elements having less than 8 electrons in the outermost shell are chemically reactive. Hence, they combine with other atoms of elements by means of chemical bonds so as to attain stable octet. So, they do not exist independently but exist in combined states as molecules. Thus, the Cosell-Lewis approach provides an explanation for the requisite of formation of bonds. Later in 1916, Cosell and Lewis developed the electronic theory of valence or theory of chemical bonding to explain the chemical bond formation between the two atoms. According to electronic theory of valence, every atom tries to attain octet in its valence shell by losing or gaining or by sharing of electrons. This is known as the octet rule. Only valence electrons are responsible for the formation of chemical bond. Except valence electrons, the remaining part of the atom, that is the nucleus, with the inner shell electrons, is called kernel. Lewis proposed simple notations to represent valence electrons in an atom. These notations are called Lewis symbols. As per Lewis symbols, the number of valence electrons of an element are represented as dots around the symbol. Let's look at the Lewis symbols of the elements lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon as shown. The number of dots around the symbol gives the number of valence electrons. These valence electrons are useful to calculate the group valence of the element. The group valence of an element is equal to number of valence electrons of an element, or 8 minus the number of valence electrons. This is the significance of Lewis symbols. Now, let us look at the formation of ionic bond or electrovalent bond, which was explained by Cosell by considering the following facts. Halogens, which are highly electronegative, and alkali metals, which are highly electropositive, are separated by noble gases in the periodic table. Hence, halogens gain an electron, whereas alkali metals lose an electron to form negative and positive ions respectively.
Metals losing electron and non-metal gaining electron. So मैग्नीशियम एंड एक्स मैंने हेलोजन, तो मैग्नीशियम या कोई भी मेटल जब नंबर ऑफ इलेक्ट्रॉन लूज करता है तो वो सॉलिड में चेंज हो जाता है, यानी कि आयनिक बॉन्ड और इलेक्ट्रोवैलेंट बॉन्ड में मेटल्स एंड नॉन मेटल्स लूजिंग एंड गेनिंग इलेक्ट्रॉन्स होता है. तो इलेक्ट्रोस्टैटिक फोर्स ऑफ द अट्रैक्शन दैट होल्ड इन द टू अपोजिट चार्ज आयंस टुगेदर इज नोन एज इलेक्ट्रोस्टैटिक फोर्स. फॉर एग्जाम्पल आयनिक बॉन्ड फॉर्मेशन इन सोडियम क्लोराइड. अगर हम बात करें सोडियम क्लोराइड में बॉन्ड फॉर्मेशन की, तो वी नो दैट कि सोडियम के इनर में 2, आउटर में 8 एंड आउटर में 1 इलेक्ट्रॉन होगा. अगर ये इस एक इलेक्ट्रॉन को लूज करके क्लोराइड को दे देता है, क्योंकि क्लोराइड के पास में आउटर में 7 इलेक्ट्रॉन है, तो सोडियम अपना 1 इलेक्ट्रॉन लूज करेगा एंड क्लोरीन अपना 1 इलेक्ट्रॉन गेन करेगा. तो जब ये ट्रांसफर होगा 1 इलेक्ट्रॉन का, तो सोडियम पर चार्ज आ जाएगा पॉजिटिव आयन बिकॉज इट लूज द इलेक्ट्रॉन. सो सोडियम आयन में चेंज हो जाएगा एंड क्लोराइड when gain the electron it become chloride minus ion. So by losing the metal it having positive charge and by gaining the non-metal it having negative charge. So it is the bond formation of electrovalent or ionic compounds. Both they have Na and Cl इलेक्ट्रोस्टैटिक फोर्स, जिसकी वजह से दोनों ही एटम एक दूसरे की तरफ अट्रैक्ट होते हैं. इसी फोर्स को हम कहते हैं इलेक्ट्रोस्टैटिक फोर्स ऑफ अट्रैक्शन. यही इलेक्ट्रोस्टैटिक फोर्स ऑफ अट्रैक्शन दोनों एटम्स को बाइंड करता है, जिसकी वजह से दोनों के दोनों एटम न्यूक्लियर बॉन्ड बनाते हैं. इसी बॉन्ड को हम कहते हैं इलेक्ट्रोवैलेंट बॉन्ड और आयनिक बॉन्ड्स. क्योंकि सोडियम पे पॉजिटिव चार्ज है जिसको ये लूज करता है और नेगेटिव क्लोराइड पे नेगेटिव आयन है जिसे वो गेन करता है. तो जो आयंस फॉर्मेशन होंगे वो पॉजिटिव आयन की वजह से एंड नेगेटिव आयन की वजह से एक इलेक्ट्रोस्टैटिक फोर्स ऑफ अट्रैक्शन जनरेट हो जाता है. इसी फोर्स को हम इलेक्ट्रोस्टैटिक फोर्स ऑफ अट्रैक्शन भी कहते हैं.
Calcium chloride, magnesium oxide, and other ionic compounds. On the basis of Cosell and Lewis' approach towards chemical bond, we can explain the factors that affect the formation of ionic bond. The formation of ionic bonds depends upon the following 3 key factors. First, the ease of formation of a cation. Second, the ease of formation of an anion. And finally, the arrangements of the positive and the negative ions in the ionic solid. Let us understand this by considering the formation of sodium chloride. In the formation of sodium chloride, sodium loses 1 electron and attains the configuration of its nearest noble gas, neon. The amount of energy required for the ionization of a neutral atom, which is sodium atom in this example, is called ionization enthalpy. It is always endothermic. Similarly, chlorine accepts 1 electron to attain the configuration of its nearest noble gas, argon. The amount of energy liberated for the gain of electrons by chlorine atom is said to be electron gain enthalpy. It is represented as delta EGH. It is defined as the enthalpy change when a gaseous atom gains an electron. Note that the electron gain enthalpy may be exothermic or endothermic. Thus, sodium forms a positive ion, that is a cation, whereas chlorine forms a negative ion, that is an anion. Due to the strong electrostatic forces of attraction between these oppositely charged ions, they are held together to form sodium chloride. Now let us understand how ionization enthalpy and electron gain enthalpy affect the formation of an ionic bond. The ease of formation of a cation depends on the magnitude of the ionization enthalpy. Lower the ionization enthalpy, easier the removal of electron, and hence greater is the ease of formation of cation. Similarly, the ease of formation of an anion depends on the magnitude of the electron gain enthalpy. More negative is the electron gain enthalpy, greater is the ease of formation of the anion. Hence, we can conclude that lower the ionization enthalpy and higher the negative value of electron gain enthalpy, greater is the ease of formation of an ionic bond. The resultant ionic compound consists of regular and orderly arrangement of oppositely charged ions in three-dimensional region, held by strong electrostatic forces of attraction. This means that each cation is surrounded by a fixed number of anions, and each anion is surrounded by a fixed number of cations. In a crystal of sodium chloride, each sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium ions as shown here. The difference in the crystal structures of different ionic compounds is attributed to the size of ions, their packing arrangements, and other factors. Finally, a requisite number of oppositely charged ions combine to form a crystal lattice. This process involves the liberation of energy. The higher the amount of the energy released, the greater the stability of the ionic compound. The stability of an ionic compound can be predicted by calculating the total enthalpy change in the process. In ionic solids, the sum of the electron gain enthalpy and the ionization enthalpy may be positive. But still, the crystal structure is stabilized due to the energy released during the formation of the crystal lattice. For example, in the gaseous state, the ionization enthalpy for the formation of Na+ from sodium is plus 495.8 kJ per mole, while the electron gain enthalpy for the formation of a chlorine ion is minus 348.7 kJ per mole. The sum of the two, which is 147.1 kJ per mole, is positive. But this is compensated by the energy released during the formation of the crystal lattice of sodium chloride, which is minus 788 kJ per mole. The overall energy released is the sum of 495.8 minus 348.7 and minus 788, which results in minus 640.9 kilojoules per mole. Since energy is released in the process, it makes the crystal lattice more stable. Thus, the magnitude of energy released during the formation of crystal lattice, called lattice enthalpy, provides a measure for determination of the stability of the ionic compound. Thus, lattice enthalpy plays a vital role in the formation of ionic compounds. Lattice enthalpy of an ionic solid is defined as the energy required to completely separate 1 mole of a solid ionic compound into gaseous constituent ions. For example, the lattice enthalpy of sodium chloride is 788 kilojoules per mole. This means that the energy required for the separation of 1 mole of solid sodium chloride into 1 mole of gaseous sodium ion and 1 mole of chloride ion is 788 kilojoules per mole. Langmuir refined the Lewis postulates and introduced the term covalent bond. The bond formed by the mutual sharing of electrons between the combining atoms of the same or of different elements is called a covalent bond. During covalent bond formation, each atom tries to attain octet, that is, 8 electrons in its valence shell, or duplet, 2 electrons in the first shell. The formation of covalent molecules can be understood from the Lewis dot structures. In the Lewis dot structures, the valence electrons of all the bonded atoms of a molecule are represented by dots. The following conditions are to be satisfied for the formation of a covalent bond in a molecule. Each of the bonded atom must contribute equal number of electrons to the shared pair. A bond is said to be formed when an electron pair is shared between the bonded atoms. All the bonded atoms must attain the nearest inert gas configuration as a result of sharing of electrons. Let us understand the formation of chlorine molecule by writing Lewis dot structure. The electronic configuration of a chlorine atom is neon 3s2 3p5. It has 7 electrons in its valence shell. Hence, it needs 1 more electron to attain the nearest inert gas configuration of argon. Therefore, each chlorine atom contributes 1 electron for sharing, and this electron pair is shared mutually by both the chlorine atoms. This shared electron pair joins 2 chlorine atoms together in the chlorine molecule. That is, if 1 electron pair or 2 electrons are shared between 2 bonded atoms, a single bond is said to be formed. Similarly, let us look at Lewis dot structures which depict the formation of covalent bonds in methane and carbon tetrachloride. Now, let us understand the formation of the oxygen molecule by writing the Lewis dot structure. The electronic configuration of oxygen atom is helium 2s2 2p4. It has 6 electrons in its valence shell. Hence, it needs 2 more electrons to attain octet. When 2 oxygen atoms approach each other, each of the oxygen atom contributes 2 electrons for sharing. Both the oxygen atoms mutually share these 2 electron pairs and attain the nearest octet configuration of neon. As the 4 electrons in 2 electron pairs are shared between 2 oxygen atoms, the 2 oxygen atoms are said to combine by a double bond in the oxygen molecule. Similarly, we can show the formation of carbon dioxide, ethylene, C2H4 molecules by Lewis dot structures as shown. Let us understand the formation of nitrogen molecule using Lewis dot structure. The electronic configuration of nitrogen atom is helium 2s2 2p3. It has 5 electrons in its valence shell and needs 3 more electrons to attain octet. When 2 nitrogen atoms approach each other, they mutually share 3 electron pairs and attain the nearest inert gas configuration of neon. As 6 electrons, that is, 3 electron pairs are shared between 2 nitrogen atoms, the 2 nitrogen atoms are said to join by a triple bond. Similarly, we can show the formation of acetylene, C2H2, and carbon monoxide molecule by Lewis dot structures as shown. Let us look at certain other important steps to be adopted while writing the Lewis dot structures for a molecule or an ion. In case a covalent molecule is formed between different atoms, then the atom with the least electronegativity is placed at the center, and other atoms will be placed at the terminal positions as shown here for a carbon dioxide molecule. Now, count the number of valence electrons available for bonding. In case of a molecule, count the total number of electrons present in the valence shell of all the bonded atoms. In case of ions, that is anions and cations, for each negative charge, add 1 electron to the total number of valence electrons, and for each positive charge, subtract 1 electron from the total number of valence electrons respectively. While writing a Lewis structure, it is always better to know the symbols for the respective bonded atoms or the combining atoms while you have to guess the skeletal structure of the molecule. This makes the distribution of the electrons between the bonded atoms easier. Among the valence electrons available for bonding, shared pair of electron forms a single bond between two bonded atoms, and the remaining electron pairs present on the respective bonded atoms are either used for the formation of multiple bonds or remain as lone pairs. Finally, each atom should attain octet in its valence shell, except hydrogen, which attains the stable duplet configuration. Now let's see how to write the Lewis dot structure for carbonate ion by adopting the above-mentioned steps. First, let us calculate the total number of valence electrons in the carbonate ion shown here. The number of valence electrons in carbon is 4, whereas the number of valence electrons in oxygen is 6. As 3 oxygen atoms are present, the number of valence electrons in 3 oxygen atoms is equal to 18. As 2 negative charges are present on the carbonate ion, add 2 to the total number of valence electrons present in carbon and oxygen atoms. The total number of valence electrons here is 22. Hence, the total valence electrons in carbonate ion is 22 plus 2 equal to 24. In the carbonate ion, as carbon is less electronegative, it is placed at the center, whereas 3 oxygen atoms are placed around it at the terminal positions. The skeletal structure of carbonate ion is as shown. Now let us draw a single bond between the central carbon atom and each of the oxygen atoms. This, however, doesn't complete the octet on carbon, if the remaining 2 electrons on this oxygen remain as lone pair. Hence, a double bond between the carbon and the oxygen completes the octet. This results in the following Lewis dot structure. Now let's see how to write the Lewis dot structure for ammonium ion. First, let us calculate the total number of valence electrons. The number of valence electrons in nitrogen is 5, whereas the total number of valence electrons in 4 hydrogen atoms is 4. And as 1 positive charge is present on the ammonium ion, subtract 1 from the total number of valence electrons present in nitrogen and hydrogen respectively. That makes it 9. Hence, in the ammonium ion, the total number of valence electrons is 9 minus 1 equals 8. In the ammonium ion, nitrogen is placed at the center, and the 4 hydrogen atoms are placed around it at the terminal positions. The skeletal structure of ammonium ion is as shown. When each hydrogen is bonded to nitrogen by a single bond, nitrogen attains octet and hydrogen attains duplet respectively, resulting in the shown Lewis structure.